Okay, so our next example, page 359, number 78, is another sinusoidal graph, but this time we're talking about a turntable that has a record on it, and someone has shot an arrow straight down vertically onto the edge of the record. Then what has happened is a motion detector has been set up over here, and it is 60 centimeters from the turntable or the edge of the record. So then we have a record that's sitting right around there, and we have that arrow that's shot right on it at that corner. And what's going to happen is someone's going to turn the record player on, and the turntable and the arrow are going to move away from the detector and keep coming back around like that. So the question is, if the turntable is 25.4 centimeters in diameter, find the amplitude. Well, the amplitude is half the distance from the midline. So if this arrow is coming around, the maximum it is going to be, the maximum distance away from the detector, is the diameter. So the amplitude is going to be half of that, which will be the radius. So we can find the amplitude by taking half the diameter. So that's going to be half of that 25.4. So we get 12.7 centimeters. So the next thing we're asked to do is to find the period of the arrow by analyzing the data. Now you'll notice on the table that the one thing I can definitely be sure of is the minimum value, because it's given in the problem is 60 centimeters. And it hits that at 1.8 seconds and again at 3.6 seconds. So the period is going to be the time elapsed between those 2 points. And I just have to find the period. I just have to find the distance between them. And I'm sure most of you see that 1.8 is half of 3.6. So it's just going to be 1.8 seconds. So then the next part asks us to model the arrow as a sinusoidal function. So we already have A and we have the period. So we have to find our B, our C, and decide which sinusoidal function that we want to use. So in this case, because it starts at a minimum, goes the whole way around back to the minimum, the best function to use is the negative cosine. So we're going to use this basic function, d of t equals negative a cosine of b times t minus capital T plus c. The other nice thing that is great is the fact that for capital T, we can let that equal 0, because it's starting at time 0. At the nearest point it can be to the detector. So we don't have a shift in that way. We already have A. Our A is 12.7. We have B, so we can find B because we have P, which is 2 pi over P. So we're going to take 2 pi divided by 1.8, which we'll just leave as pi over 0.9. And then we have to find C. C is defined as taking the maximum distance plus the minimum distance and dividing that by 2. Now C is not going to be perfect, but we'll use what we have in the table, and it is pretty close. When you see the model, you'll see it's close enough. If you notice, we do have the maximum occurs right in between those 2 times and again here. So we can just estimate it that it is about 85. So I'm just going to leave it at the 84.7 because it's going to go slightly past 84.7 and come back to 84.7 in 0.2 of a second. So for our model, using the 84.7 will be close enough. So for that, our C, we're going to take 84.7 plus the 60 and divide that by 2. So we get a C of 72.4. And I'll round that up to 0.4. It comes out to exactly 3.5. But because it's a little off, I'm going to round it up so it gives us that little bit of missing distance. So now we can fill in our function. So d of t is going to be negative 12.7 times the cosine of pi over 0.9 times t, and then plus our c, which is 72.4. Now we're asked to graph our function with a scatter plot to show that our model is a successful model. So when you want to go, what you want to do now is go in your graphing calculator, and there's our model. And I left the 3.5 there. So let me change that to the 0.4. Oops. And you can see I have my plot open as well. And I'll show you that I went under Stat, Edit. I set up my List 1 and List 2 for the table. I opened my scatter plot, my plot 1, with a scatter plot, the two lists. And now I'm just going to press Zoom 9 to give me a nice scatter plot. And then you can see my models going through. And as you notice, my model, it hits every single data point. So that minimum little error we have for our maximum is pretty good. And you can see it's just slightly above where those 2 points are at each maximum, exactly what we'd like. So our model is spot on. So we have a great sinusoidal model to show how that arrow is moving around the turntable.